In this video, we are going to talk about matrix operations. As you may have guessed from our other videos, matrices become very important. In fact, we're going to use matrices basically almost in every problem we do for the rest of this class. So another thing we should talk about, in addition to matrices, we're going to refer to numerical quantities. So by numerical quantities, I mean non-vector, non-matrices, just a number as scalars. For the most part, these are real numbers. So real numbers we will call scalars, but also they can be complex numbers. And in my videos, I will be referring only to real numbers. So the first thing we will look at is matrix addition and scalar multiplication, which you have probably seen before. We will look at vectors in Rn, which if you've had vector calculus, you've seen this before. We will look at matrix multiplication. Again, you've probably seen this, but we're going to look at it, and we're going to look at it with respect to our linear systems of equations. And then we will look at other formulations of matrix multiplications. So the formula you're used to seeing, you do need to know, but you need to be familiar with these other forms as well, because they will come in handy. So it's critical you're able to go from one form to the other and choose the form that'll suit the problem best. We are going to start with matrix addition and scalar multiplication. So matrix addition, if you have a matrix, and matrices generally are represented with capital letters, and then their elements, the things inside the matrices, are represented with lowercase elements, and they're represented with a lowercase and an ij. I tells you which row, and j tells you which column. So for an A2, 3, that's the second row, third column. In this matrix, it would be the number 1. So we have the matrix A and the matrix B, and they are both m by n. So m rows and columns. Then A plus B is the m by n matrix, so the addition gives you the same size matrix C equal to C sub ij, where C sub ij is equal to A sub ij plus B sub ij. In other words, we add component by component. So an example, if this is A and this is B, then A plus B is equal to, well, for the first component here, the 1, 1 component of our resulting matrix of A plus B will be the 1, 1 component of A added with the 1, 1 component of B. So we have 1 minus 3. For the 1, 2 component, that's the first row, second column, we will look at the 1, 2 component of A added with the 1, 2 component of B. So that will be 2 plus 1. And then for the 1, 3, that's the first row, third column, we will add the 1, 3 component of A, which is negative 1, and the 1, 3 component of B, which is 2. And then to get to the 2, 1 component, that's the second row, first column, we'll add the 2, 1 component of A with the 2, 1 component of B. The 2, 2 component will be the 2, 2 of A and 2, 2 of B added together. And then the 2, the second row, third column, 2, 3 component is the 2, 3 of A added to the 2, 3 of B. So our final resulting A plus B matrix is going to be 1 minus 3 is negative 2, 2 plus 1 is 3, negative 1 plus 2 is 1, 2 plus 0 is 2, 3 minus 4 is negative 1, and 0 plus 1 is 1. And just a note, A plus C, since A and C are different sizes, A plus C is undefined, right? Because here you would have something in the third column, there's nothing to add to in C, so it's undefined. Next, we have scalar multiplication, so multiplying a matrix by a scalar, such as the number 2, for example. So if A is our Aij and it's m by n, and R is a scalar, Ra is the matrix D, same size, which is just every component of A multiplied by R. So here we have A, we multiply by 2, it'd be 2 times 1, 2 times 2, 2 times negative 1, and then going for the second row, 2 times 2, 2 times 3, and then 2 times 0. So our resulting matrix will be 2, 4, negative 2, 4, 6, 0. And then I also have this additional 2a plus b, so I added 2a plus b here. So I adding these together, I get negative 1, 5, 0, 4, 2, and 1. The next topic we have is vectors in Rn. So a point in n-dimensional space is represented by an ordered n tuple of real numbers. So x equals x1, x2, up to xn, and is called an n-dimensional vector and will be written in this column form, so our vector x is equal to x1, x2, up to xn. And the set of all n-dimensional vectors with real components is called the Euclidean n-space. So for example, here we have our n-tuple. We have it written in column form. So if n is equal to 2, that's our normal 2-space, our normal Euclidean graph that we plot x versus y. And so our first point might be the ordered pair 1, 2, the second point might be 3, 2, and our third point will be 2, 3. And again, you can plot them if you'd like, as you normally would on a Cartesian coordinate system. But here, our x, then our first point, we're going to represent as a column vector 1, 2, y is equal to 3, 2, and z is equal to 2, 3. And again, because they're ordered pairs, y and z, they have the same components, but they are not equal because the components are in different orders. The 3 comes before the 2 here, and in z, the 2 comes before the 3. And R3, that's our three-dimensional space that you are familiar with. And we have three tuples like 1, 2, 3, 3, 2, 1, and 2, 3, 1. And so our x in a column vector form looks like 1, 2, 3, y is 3, 2, 1, and z is equal to 2, 3, 1. If we have R4, we have ordered 4 tuples like 1, 2, 3, 4. And our x vector here would be 1, 2, 3, 4. And in general, Rn is the vector. And I often forget to put the little vector sign on top, so I apologize in advance, but many books do distinguish vectors by either making them bold or put this little line, the arrow on top. So our column vector is just x1, x2 up to xn, where x1, x2, all the way up to xn are real numbers. So this is our Rn, our n-dimensional Euclidean n-space. And we call this R2, which is two-dimensional because there are two dimensions, x and y, or the x-coordinate, the y-coordinate. This is R3, it's three-dimensional. R4 is four-dimensional, and Rn has n dimensions, and is also called the Euclidean n-space. Now that we've talked about matrix addition and scalar multiplication and vectors in Rn, we can talk about matrix multiplication. So if we have a matrix A and B, and their dimensions, so A is m by n and B is r by s, we can define A times B if n is equal to r. So these middle two dimensions need to match. So A is m by n and B is equal to, this should also be n, matches the n, the r matches the n by s. And we can find that by C, where the components are equal to the sum. And if you look at this, the sum index goes from k equals 1 to n. The k here, this is the row, this is the column, is going over the different columns. So it's holding I constant, and it's going through the column. So it's going down the row. And here, B sub jk, so k is what's changing. That's the row indice, and j is held constant. So if the row indice is held constant and j is iterating, the column constant, we're going down this column here. We will do an example of this rule, but also before we go to that, I do want to mention that this definition here is consistent with using matrices to represent linear systems. So we'll come back to this as well. And now we'll do an example. We'll take A equals 1, 2, 2, 3, and B is equal to negative 3, 2, 1, negative 2. We also have C equals 1, 0, negative 2, 0, 1, 1, and D equals 2, 3, 1, negative 1, 2, 1, 1. So if we want to multiply A times B, so here we have the formula for C sub ij is equal to the index from k equals 1 to n, A sub ik, B sub kj. So for example, if we want C sub 1, 1, so in this case I is equal to 1 and j is equal to 1, for our formula we have k equals 1 to n, A sub 1k, and B sub k 1. Remember, I and j are both equal to 1, so I plug that in here. So as I let my index run, k go from 1 to n, when k is equal to 1, that will be A sub 1, 1, B sub 1, 1, and when k is equal to 2, that will be A sub 1, 2, B sub 2, 1. And then looking at my matrix, A sub 1, 1 is 1, B sub 1, 1 is negative 3, so I multiply those together, and I add them with B sub 1, 2, first row, second column, that's 2, times B sub 2, 1, second row, first column, that's 1. And so this here is my first entry, my C sub 1, 1. I have the other calculations for C1, 2, and C2, 1, and C2, 2 broken up here and written out here, and then the final summation here. The easy way to remember this is you're probably not going to expand this formula out every time, but you're going to think of taking the rows of A multiplying by the columns of B. So the first row of A multiplied by the first column of B is your 1, 1. The first row of A times your second column of B is your element C, 1, 2. The second row of A, first column of B, is going to be your element 2, 1. Okay, so whatever the row is for A, that's the index into the row for matrix C. Whatever column you take for B, that's the index for the column in matrix C. Then you can see I have AC. So I'll do this just kind of multiplying row by column, AC. So for the first row, first column, I take first row of A, multiply first column of C. So I have 1 times 1, 2 times 0. For the first row, second column, I'm going to take the first row of A, multiply by the second column of C. So I have 1 times 0 plus 2 times 1. For the first row, third column, first row of A times third column of C. So 1 times negative 2, 2 times 1. And then here for the second row of my product matrix, second row, first column, it's second row of A, first column of C. So I have 2 times 1, 3 times 0. Second row, second column, so second row, second column, 2 times 0, 3 times 1. And then for 2, 3, it's second row, third column. So 2 times negative 2 plus 3 times 1. And then I've added that here. I also have the matrix C times D, and you can check this out. C times D, let me do this. For 1, 1, first row, first column. 1 times 3 is 3, then you add the 0, minus 2 is equal to 1. First row, second column, that will be first row times second column. So 1 times 1 is 1, plus 0, minus 2 is minus 1. Then for the second row, first column, so that's the second row, first column, 0, negative 1 plus 1 is 0. Second row, second column, that's multiplying the second row, second column. 0, 2 plus 1 is, oops, that should be a negative, is negative 1. Then D times C, this is first row, first column. So first row of D times second column is C. So 3 times 1 is 3, plus 0 is 3. First row, second column, so that's first row, second column. 3 times 0 and 1. First row, third column, first row, third column. 3 times negative 2 is minus 6, plus 1 is negative 5. So second row, first column, second row, first column. Negative 1 plus 0, that's negative 1. Second row, third column, that's 0 minus 2. And then second row, third column, that's 2, minus 2 is 0. And then the last third row, first column, that gives us 1. Third row, second column, that gives us 1. Third row, third column, that gives us negative 2 plus 1 is minus 1. So you will notice that CD does not equal to DC, and in general, matrix multiplication is not commutative. And next, I want to show how this definition of matrix multiplication is consistent with how we've been using matrices to represent linear systems. So we can represent our linear systems, as we said, with this coefficient matrix, and now we can multiply times our vector of unknowns. So x1, x2, xn, those are our unknowns in our linear system. And then that's equal to, here, this is kind of our solution vector, our b vector, y1 to y2. And if you multiply this matrix out, right, so if we go a1, x1, a12 times x2 up to an times xn, that should equal to y1. This is exactly the same sort of notation and representation. I have an example that uses this matrix multiplication. Express each of the linear systems, so I have one linear system here and another linear system here, as a matrix equation, and use the matrix multiplication to express x1, x2, and x3 in terms of z1 and z2. So express x1, x2, and x3 in terms of these variables here, z1 and z2. I will start by expressing my first system in terms of matrices. So I have x1, x2, and x3 is equal to my coefficient matrix is 2 minus 1, minus 3, 2, and 1, 3, times my unknowns, which is y1, y2. My second linear system is y1, y2 is equal to my coefficient matrix, negative 4, 2, 3, 1, times my unknowns, z1 and z2. Now, if I want to express x1, x2, and x3 in terms of z1, z2, I can plug in this matrix, the coefficient matrix times z1, z2 for y1, y2 over here. So I have x1, x2, x3 is equal to my 2 minus 1 minus 3, 2, 1, 3 times y, which I'm going to plug in this matrix, negative 4, 2, 3, 1 times z1, z2. So now I can multiply these two matrices and I get my 11, 3, 18 minus 4, 5, 5. So x1, x2, x3 is equal to this matrix here, my minus 11, 3, 18 minus 4, 5, 5 times z1, z2. So just to kind of restate this definition here, so our general system of linear equations can be represented in matrix form, ax equals b, where A is the coefficient matrix, so you just take the A1, A2 up to A1n, and the A21, A22 up to A2n, etc. And then your x is equal to your unknowns, x1, x2 up to xn, and then your b is this vector here, b1, b2 up to bm. This next example asks me to solve the matrix equation ax equals b, where A is this matrix 1, 3 minus 1, 2, 5 minus 1, 2, 8 minus 2. X, again, is just our x vector, which is x1, x2, x3. And b is equal to 2, 6, 6. So what I can do to solve this, I can use basically the same technique I used for systems of linear equation. I can look at my augmented matrix, which is A with B. So I have AB here, 1, 3, negative 1, 2, 2, 5, negative 1, 6, 2, 8, minus 2, 6. And I do my elementary row operations, which I'll let you confirm, until I get to this echelon form matrix, which is 1, 3, minus 1, 2, 0, minus 1, 1, 2, 0, 0, 2, 6. So back solving, this gives me, this is x1, x2, x3. 2x3 is equal to 6, which gives me x3 is equal to 3. And then I have, this is x1, minus x2 plus x3 equals 2. So plugging in 3 for x3, I get x2 is equal to 1. And then I have my x1 plus 3x2 minus x3 is equal to 2. So solving, plugging in for x2 and x3, I get x1 equals 2. So my solution for x is equal to x1, which is 2, x2, which is 1, and x3 equals 3. So you can verify this. If I multiply my matrix A by this vector x, I should be able to get B. And this is the unique solution. Now that we've gone through matrix multiplication, which is probably the definition you've been familiar with from middle school or high school, we want to get familiar with some other formulations of matrix multiplications that you may not have seen before, but are important and are very common and useful in linear algebra. So first, we often write our matrix A as a vector of column matrices. So A1 is essentially the first column of matrix A, A2 is the second column of matrix A, up to AN, which is the nth column of matrix A. So for example, if A is equal to the matrix 1, 3, 6, 2, 4, 0, then we can write A is equal to A1, A2, A3, where A1 is the column vector 1, 2, A2 is the second column vector of A, which is 3, 4, and A3 is the third column vector of A, which is 6, 0. And the reason why this is so useful is this theorem here. If we let A equal to the matrix A1, A2 up to AN, and it's an m by n matrix whose jth column is A sub j, then we let x be the n by 1 column vector, which looks like x equals x1, x2 up to xn, then the product AX can be expressed as x1 times a1 plus x2 times a2 up to xn times an. So for example, if A is again our column vector, our matrix 1, 3, 6, 2, 4, 0, and x is equal to x1, x2, x3, then ax, which I have done the multiplication out right over here, that would be x1 plus 3x2 plus 6x3, and then for the second row, that would be 2 times x1, 4 times x2 plus 0x3. This is equal to, if you look at this, will be equal to x1 times the first column plus x2 times the second column plus x3 times the third column, because if you multiply this out, you are going to get x1 times 1 is x1, and then we have 2 times x1 plus 3 times x2, 4 times x2 plus 6 times x3, and then 0. And then when you add term by term, you're going to get x1 plus 3x2 plus 6x3, and then the second row is 2x1 plus 4x2 plus 0, which is exactly the same thing that we got when we did the direct matrix multiplication. So this theorem here is really useful, and you should be really comfortable expanding this matrix multiplication, this AX, expanding it out in this way. And one of the big other ways of looking at this is when we look at AX equals B, being rewritten in this form, x1 times the column vector a1, x2 times the column vector a2, plus xn times the column vector an equals b, then solving this matrix equation is the same as showing that B can be written in terms of columns of A. And in fact, B can be written as a linear combination of columns of A. So this is another important way. It's just a restatement of the theorem. It's important to understand both of these, the theorem and also this implication, that to solve this matrix equation, that means B can be written as a linear combination of the column vectors of matrix A. And to look at another example of this, let's say we want to have, we have column vectors 1, 2, 2, 3, 5, 8, negative 1, negative 1, negative 2, and we want to know what coefficients we can multiply each vector, each of these column vectors by, in order to have the resultant vector 2, 6, 6. Or stated another way, how can we write 2, 6, 6 as a linear combination of these three vectors? What coefficients need to go in front? And we know how to solve this because we can just use the same techniques we used for our systems of linear equations. In other words, this is equivalent to the AX equals B problem, where A is equal to just concatenating the column vectors, X is equal to our unknowns, and B is equal to this 2, 6, 6. And we solved this in a previous example, so I wrote down, like in this video, we solved this previously in this video, so I have the steps here just to remind you. And what we got is X equals 2, 1, 3 is the unique solution to this matrix equation. So if we multiply A times X, we will get B. But as far as solving this problem, writing 2, 6, 6 as a linear combination of the three vectors, that means if we take the 2 and multiply 1, 2, 2, plus the 1 and multiply the 3, 5, 8, and the 3 and multiply by 1, negative 1, negative 1, 2, you will see that we get this vector here, the 2, 6, 6. And you will see that this question, can I write a vector like 2, 6, 6 as a linear combination of other vectors? And if I can, what are the coefficients? This becomes a very important question throughout this whole topic of linear algebra. So these examples here where we're doing these linear combinations, they're important to be very solid and have a good understanding of them. Here is another example. Here we have a linear system. We want to express this linear system in the form AX equals B. We want to solve using Gaussian elimination and determine how to represent B as a linear combination of the columns of A. So this is very similar to what we just did in the last problem. Here I have my matrix A, my matrix of coefficients, my 2, my -1, my 1, my 1. My x, again, are my unknowns, x1, x2, and b is equal to 3, 3. So we're solving ax equals b. And again, we can treat this and use Gaussian elimination just like we did for a system of linear equations. Actually, we are solving linear equations. So you can verify that this will get me to this echelon form matrix, which is 2, -1, 3, 0, -3, -3, which tells me this is x1, this is x2. -3x2 is equal to -3, which means x2 is equal to 1. And then we have 2 times x1 minus x2 is equal to 3, which gives me x1 equals 2. So this equation is simple enough that you probably could figure this one out kind of by whatever random means you want, even maybe just test, guess, and try. But the thing is you do want to get this technique down. The important thing isn't the algebra here, because you could have done that in middle school. The important thing is understanding how this all connects. So here we have that x1 is equal to 2 and x2 is equal to 1 is a solution to the system of equations. And also, the other very important part is viewing this as b, 3, 3, can be written as a linear combination of the column vectors of A, that is 2, 1, and -1, 1, and the coefficients will be 2 and 1. Here is our last theorem. Let A be an m by n matrix and B be a matrix which is equal to the column vectors b1, b2 up to bs, and B is an n by s matrix whose kth column is bk. Then the jth column of AB is ABJ, so that AB is equal to AB1, AB2 up to ABS. And here's an example. So if A is equal to the matrix 2, 6, 0, 4, 1, 2, and B is the matrix 1, 4, 3, 5, 0, 2, 1, 3, then B1 is equal to the first column vector, which is 1, 4, B2 is equal to 3, 5, B3 is equal to 0, 2, and B4 is equal to 1, 3, which I guess I should write down. So then I can multiply A times B out, and I will get this matrix here. I didn't actually do all the addition yet. But I can get the same thing by multiplying AB1. So here I have my matrix A, and here's B1, the first column vector of B. And I will get my 2 times 1 plus 4 times 6, my 0 times 1 plus 4 times 4, my 1 times 1, and my 2 times 4. So if you look at that, if you compare this to the first column of AB, they're exactly the same. I did the same thing for AB2, so I have my A and my second column of B. I multiplied and did the matrix multiplication, and you can see it's exactly the same as column AB, the second column of AB. And you can do the third and fourth column as well. For review, I have 3 problems for you to try. So pause the video, give them a try, and then on the next slides, I will have solutions for you. We've gone over the material for our video. First, we did matrix addition, and we multiplied a scalar times a matrix. We looked at vectors in Rn, and then we defined matrix multiplication using this very common definition of how you multiply matrices, and we saw that this definition was consistent with how we were using matrices to represent linear systems. We concluded by looking at other formulations of matrix multiplication. In particular, we found that if we consider A a bunch of column vectors, then we can consider the product AX can be expressed as x1, our first unknown, times the first column vector of A, plus x2 times the second column vector of A, up to xn times the third column of vector A. And we have this example here to show us that AX can be considered x1 times the first column vector, plus x2 times the second column vector, plus x3 times the third column vector. And we noted that that means this equation, AX equals B equation, is the same thing as asking if B can be written as a linear combination of the column vectors of A, as we have here. This would be a linear combination, this x1 times 1, 2 plus x2 times 3, 4 plus x3 times 6, 0 is a linear combination, and we're seeing if it can be equal to B. And then last we had this theorem where we had two matrices. We can consider that A times column, the first column of our second matrix, A times the second column of our other matrix B, up to A times the sth column of our matrix B. This is the solution for the first problem. Here is the solution for the second problem. And here is the solution for the third and last problem.